In this video, we're going to look at resistance for GCSE electricity. Resistance is the opposition to motion of electrons, or it's a force that's trying to stop the electrons moving. Now, I wouldn't really use force. It's probably not the best word to use, but if you're really struggling to get the idea across, you could use that word. It's not the end of the world. How do we define it formally? It is formally defined as the ratio of potential difference to current. And this can be thought informally as push over flow. So it's the amount of force we need to make the electrons move, or the amount of energy we need to make the electrons move. It's probably better to talk in terms of energy because potential difference is the energy per unit charge. So what actually causes it? Well, we need to talk about the structure of metals to really understand this. So a metal has a regular lattice and it has delocalized electrons. And as the electrons move through the metal, they will inevitably collide with the ions. So it's the collisions between electrons and metal ions that equals resistance. So here we've got a relatively low resistance. We haven't got very many collisions. Let's draw something that has a much higher resistance. So you can see there's obviously far more ions here, so that when I then have my electron moving around and colliding, it will have many more collisions. So more frequent collisions equals a higher resistance. And you can do some nice animations on PowerPoint, or you can find some nice animations on the internet to demonstrate this. It is also important to note that the electrons are going all over the place. They might even go backwards at some point. The overall current will be in one direction, but the individual electrons will actually only move a little bit of distance each time, and they'll be moving in all sorts of directions. And what's interesting to note is that the kind of speed of the current is close to the speed of light. So when you turn on your light switch, the electricity overall, the current will more or less travel at the speed of light, and it'll be a very, very fast reaction between turning on the light switch and the light coming on. However, the electrons, and at A level we'll talk about the drift velocity of the electrons, move slowly. They actually move on the order of millimeters per minute. So an individual electron, because it's doing this colliding all the time, moving backwards, it's only going to move a few millimeters every minute, or maybe centimeters every minute. Okay, so not very, very far, not very fast at all. All right, don't need to know this for GCSE, but it's interesting to talk about. So what does this mean in terms of a wire? So if I have a circuit with a wire here, well, if I have a wire that's longer, then obviously what's going to happen is there's going to be more collisions over the length of the wire. So there's going to be a higher resistance. And again, every time we talk about this, we're going to refer back to this collision between electrons and metal ions. So I'll just put this for resistance going up. Supposing I have a thicker wire, and this often trips students up. So again, they might say, well, there's more atoms there, so there's going to be more collisions. But actually what we're doing is we're creating more space for the same current. Now, because it's more space for the same current, actually what happens is the resistance goes down. So this is like saying, if you have a doorway and you've got one student trying to get through it, right, quite easy. If you then bunch loads of students up and say, right, I want the whole class to get out at the same time, there's obviously going to be a high resistance as they collide into each other. However, if you now have multiple doors, or you had a really wide door and multiple doors is just this wide door divided into multiple sections, then the same number of students can spread out and get through this with a lot less effort and a lot less collisions. So therefore the resistance goes down. And this is important because we will go on later to talk about when we have resistors in parallel and what happens to the resistance of resistors in parallel. And the resistance goes down, right? Because there's more space. This is the same as saying a wider door or a wider door split up into 3 separate doors. And of course, a longer wire would be the same as saying we've got resistors in series, in which case the resistance goes up. And you should always refer back to the rope model as well with this. The more hands you have gripping it, the more friction there's going to be, therefore the higher the resistance. And then the last thing we can talk about as well is what happens if we heat up our wire. Well, we're going to have ions with more vibrational energy, or you can just say they vibrate more frequently. And again, we're linking this back to our molecules and matter topic. So what's going to happen, there's going to be more chances of collisions, and so there's going to be more frequent collisions, and so the resistance goes up. And this, of course, is important because students need to be able to explain a bulb resistance in terms of temperature, certainly at higher tier. So there's a couple of practicals that we can do for this. One practical is to get a graph, and this is a required practical in AQA, of resistance against length of wire. And if you do this, you get a nice straight line through the origin, which makes a lot of sense. The circuit diagram for this is really simple. We have a battery or a cell. We have an ammeter in series because in order to measure resistance, we need both potential difference and current. Then we have some length of wire. And this is the one bit that students get confused about. We need a voltmeter attached to a flying lead, and we often represent it like this. And this means we can obviously change the position on the wire that we connect the voltmeter to. So we're effectively changing the length of wire that we are measuring. In fact, I've made a little mistake here as well, because this ammeter here is obviously connected to the same place each time. We would want the ammeter on, in fact, this whole thing is a bit wrong. It's probably just easier to redraw it. So here I've redrawn it correctly. So you'd actually need something like this. You'd need this to be the wire, and then you can obviously put a ruler next to it. And then you need the ammeter connected to this flying lead and also the voltmeter connected to this flying lead, but in parallel. So this way, as you change the position of this flying lead, which in reality is going to be a crocodile clip, you are changing the length that you are measuring. Now the current is always going to go through the full length, but the resistance, we are only measuring, the voltage, we are only measuring over this length of wire here. So this is the correct setup. Really quick and really simple, as long as you encourage students to unplug the cell each time, probably with the addition of a switch so that it doesn't get too hot. So this leads us nicely to the IV graph for a wire. So if we now plot current against potential difference for a wire, we get a straight line. The ratio of V over I, every single place on this line is the same, which implies that it is a constant resistance for a wire, which leads us to Ohm's law. Ohm's law is that basically the shape of this is a straight line. So V is directly proportional to I if the temperature is constant. So as long as you unplug the cell each time, the resistance will be constant for a given length of wire. If you allow the wire to heat up, then we end up with this scenario here, and the resistance will increase, which is not what we want. So obviously this doesn't come directly from this because we're changing the length, but it's a related practical where you will place an ammeter and a voltmeter in series. Sorry, a voltmeter and parallel ammeter in series, and then you will put a resistor here, or you might put a bulb here, and then you vary the potential difference across this. So you can either vary this if you have a variable power supply, or you can put in a variable resistor, and you can change the total resistance, which will change the voltage and current, and then you can plot that. So we need to do this for a wire. We also need to do it for a bulb and see what happens to the resistance. If you do it with a bulb, you will get a graph that looks like this. Sorry, no, you won't. You will not get a graph that looks like this. If I switch the axes around, you will get a graph that looks like this. I'm a bit of a fail today. You will get a graph that looks like this. So initially, the very first bit, you might say it's ohmic, it's a straight line. Then very rapidly, the potential difference increases far more than the current, and eventually the current ends up at a constant level that won't increase anymore. And that's because we have heating and we have R increasing, right? Exactly because of this here. And it's important that students understand that, certainly at higher tier. Now, sometimes in exam questions have in the past got this wrong, which is really bad. Resistance here is still V over I. So you still pick a value of V, a value of I, and you still work out this. It is not the gradient. Right? The gradient is something completely different, and it's not equal to the resistance. The resistance, you purely take a value of V and a value of I. So if you do that for 2 or 3 points along here, you will obviously see the resistance increasing because the potential difference is increasing, but the current isn't increasing. So this is getting bigger, this is staying the same. And then the very last component that we are going to look at would be a diode. And this is a special component that only allows current to flow in one direction. So for negative directions, negative potential differences, there is zero current. At low potential differences, there is zero current, and then it rapidly turns on at this point that we call the threshold voltage. So you can do the practical together with students for this, or you can just show them this. And they need to know what diodes are, what they do, what the circuit symbol is for a diode. And the uses for this really do come up in AC electricity, where we're turning AC into DC. But for now, they just need to be able to recognize this. So there we have it, resistance for GCSE.